So last time we went through some kind of basic tools, the tools of quantum mechanics for how to represent a state, how to perform basic measurements, how to compute probabilities, how to compute post-measurement states, and then we tried to motivate what a mixed state might be and why we need a mixed state. And so today I'm going to do a little bit more of this tool building for just a few minutes, and then we'll get started into the quantum epsilon machine type stuff. I'm going to do a little bit of a introduction to thinking about composite systems in quantum mechanics, which is in some ways very straightforward. Actually, Greg did a really nice introduction to the details and the depths of the tensor formalism yesterday. So I'll be doing kind of an overview of that kind of information, and then we'll head on to the research. Okay. So, just to review, or just to remind some of the people that haven't seen some of this notation before, remember that by this bracket thing, we mean that this is a vector in our Hilbert space. So this is a particular type of quantum state that's what we call a pure state, not a mixed state. And here by AB, I'm indicating that this is somehow a state over the composite system of A and B. So what do I mean by that? So A might represent something like the spin of a particular electron, and B might represent the spin of another electron. And these two states independently tell you about this electron and that electron. And these two states would live in independent or separate Hilbert spaces. They don't have to be spaces of the same size or the same type. They don't have to do with the same object or a different object. So for instance, we could construct a tensor product or a composite system thinking about the electron spin and then the position of the electron as the other component of this composite wave function. And very straightforwardly, if we have a basis for one space, a basis for another space, we write the composite basis something like this. And here's an example of a more compact notation for how we would represent the basis for two spins. So we could think of this as up, 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 down, down, up, and down, down. And just to be a little bit more precise, this is some of the shorthand that you'll often see rather than seeing things individually labeled and seeing this tensor product in between two kets. What you'll see is these two symbols jammed inside the same thing and not labeled, but it's understood that one's on the right or one's on the left. And so it refers to this subsystem or that subsystem. So sometimes you have to do a little bit of backtracking to figure out what goes with what. Okay, so a couple of examples. Well, so we already saw examples of composite system states. The basis states are examples of states in this composite system, not terribly interesting. So we can do a little bit more than that. We can form superpositions of these things. So for instance, here we have some adding and subtracting of some of these basis states, and then just a normalization. So one question you can ask is, can I, as I did before, write this overall state as something with A's on the left and B's on the right? So you see the way I've written it here, this is an A thing, a B thing, an A thing, a B thing, they're all mixed together. So can I somehow untangle things? And you can. It's straightforward to see that through just distributing this multiplication, that these two things are equal. So this is what we think of as a factorization of this representation into the A stuff and the B stuff. Okay, and so now the question is, oops, here's another state, ostensibly simpler. It only has two things rather than four things. So can we do the same game here? Well, there's only a 0 and a 1 and a 0 and a 1, so it seems like we ought to be able to finagle this somehow. Let's write out what we'd have to do. Well, we'd have to say, well, let's construct some generic superposition here, some generic superposition here as a product. Multiply all this stuff together, get all these factors out in front of the various things, and then match them up. So alpha gamma would have to equal, I guess I'm looking for, I have a half missing. The point remains that you can't have alpha delta equals 0 and beta gamma equals 0, and these things both non-zero. And the upshot is that there is no factorization, and that means that this thing is what we call, or we call this an entangled state. So a state that is factorizable we also call separable, and something that's non-factorizable or non-separable we also call entangled. And I'll just draw your attention to the fact that we ended last time talking about mixed states, which were the more general notion of state. They had to do with the ability to combine the ideas of quantum superposition and classical probabilistic mixtures. Here, we're able to define this idea of entanglement without having to resort to the more complicated space of the mixed states. We can do this simply for pure states. And in fact, it's easier to do that here. And there's a lot of complication that arises when you think about entanglement in the mixed state space. Okay, and then returning to the kind of drawing things back into the information theory world. We ended last time talking about the von Neumann entropy and coding a little bit. So let's look at a couple of these composite states. I'm giving you one that's just, and here I'm using rows to illustrate that these are mixed or density matrices. So I have one of these basis states that I showed you before, but it's outer product with itself. Okay, and that's a simple one. It looks simple. Here's a superposition. So I had a superposition and I did the same thing. And here's this entangled guy that we just saw. Yeah. And so the question for you is, and this might be a little bit too much to ask, but what are the entropies of all these things? How would you compute them? Does anyone want to venture a guess? Aside from people in the back row? Remember the definition of the entropy, or at least maybe the interpretation that we had of the von Neumann entropy? I think I said it had something to do with the measurements, or the space of different measurements that you could perform, and the entropy of the resulting measurements that you would see. So for instance, here are two good examples to keep in mind. Going back to the block sphere now. So this thing is just the state 0. And what did we decide that the von Neumann entropy of that was? You remember? 0? Because if you choose to measure spin left-right, you get a distribution of 50-50. If you measure spin, northwest, southeast, you get a distribution of more up, less down. If you measure up versus down, you get a distribution of always up, never down. So that's the minimum entropy over all the measurements that I can perform, and that has an entropy of 0. So the von Neumann entropy is 0. Okay, and then here, our other extreme example, for any old measurement that you perform, any complete measurement, you find that the entropy of the distribution is 50-50 or 1 bit. So the von Neumann entropy of this thing is 1. Okay. So let's imagine performing measurements on some of these things. Take the simple thing. So any intuition for a measurement that you could perform that might conceivably minimize the output distribution? I know we're going from kind of 0 to 40, but so what would happen if you measured in the basis that contained this basis state? Or in other words, to be a little more specific, if you remember, the measuring objects can be thought of as these labeled projectors. What if one of your projectors, let's call it A, was this projector? What would you find? Ariana, what would you find?
The probability of that coefficient of 0, 0.
Right. This is what you would use to compute that probability, and what would that probability be?
1 up. I mean, in what state?
For the simple one.
1.
Yep, 1, right. So this is a projector, which if you include it in your set of projectors that make up your measurement operator, will ensure that when you perform this measurement, you will always get an A out of your measuring device. And so you have 3 other degrees of freedom here with your other 3 projectors that you could do the easy ones. You could use the kind of computational basis, or you could kind of rotate them around and do that. You have some freedom there. Okay, so what's the upshot of that? We're after this ultimately.
So, for the first one, you're going to have 0. 1 entropy, right?
For this choice of measurement, if I include this projector, and 0 is the minimum,
yeah.
So that means that that's the von Neumann entropy, is 0. Right, okay, great. How about the next one? Possibly more challenging.
It should also be 0 because it's the pure state.
Right, and how do you know it's a pure state?
Because it's not a mixture, because you're writing it as an outer product and not that.
Exactly, I was able to write it as an outer product. And I did it explicitly, so I already did the factorization for you. So you can see that it's an outer product, therefore that means it's pure, and this means that the von Neumann entropy is 0. According to the previous argument that we were going through, you would just pick the particular projector that corresponds to exactly this state. So you'd form the projector by making an outer product of this thing with itself. And so the projector would pick up exactly that component, and it's the same as this situation, but just rotated now. Okay, and then what about this thing? This is entangled, so things are a little bit different.
It's still a pure state.
Good, still pure state, yeah. So it's different, but there are 2 different products going on. And this is something that sometimes is a little bit tricky to keep track of. There's the outer product between the 2 component spaces that's kind of buried in here. I didn't write these products. And there's the product that occurs here between this representation and dual representation of the state space. And what we're really, the relevant feature here is this one. And so it's still a pure state. I can form the projector by, well, taking this thing. Actually, this is the projector right here. Okay, so all these have von Neumann entropy equal to 0. Great. So the von Neumann entropy involved, and I said these are all kind of equivalent because going from here to here, you can imagine just rotating around. Okay, we have some pure state, we have another pure state, we're rotating around. That rotation is taking place in the composite space. But sometimes, as an observer, as an actor, you don't have access to the global system. So it may be a reasonable question, what can you do if you're able to rotate your measuring device, but only locally? You can't simultaneously rotate someone else's device far away. So what we can do is we can try to construct these Venn diagrams, which you've seen a lot of probably in this class. That's been a focus, right? Which just visually represent the amount of entropy in the composite system and in the subsystems, and then we have this notion of overlap or correlation. Okay, so we already know that the total entropy in this system, or the total entropy in this diagram, is 0, and that follows from what we just did. What do we know about the entropy of one of the local states? Well, we won't go through the details maybe, but it's pretty easy to argue to yourself that if you measure in the 0 direction locally, that there's going to be no no ambiguity in the result. So there's no entropy here. Analogously, there's no entropy here, and the only way to satisfy that is with all zeros. So there's no entropy or information anywhere. The same is true here. And the reason that that's true, it's not immediately obvious maybe, is because this is factorizable, but it's factorizable in a different way. It's not factorizable in the way that we had with red outer products earlier. This is between the two composite spaces. So I guess I could have written it more simply. As 0, and this is in the A space. I guess I'm doing superscripts. A space with 0, what, minus 1 in the B space. Okay, so here's my outer product, and this is the outer product between A and B. And so, being a little bit intuitive here, this means that you can kind of cover up this thing, do this measurement, and you'll get, if you choose this to be one of your projectors, then you'll get no entropy in the result. So the von Neumann entropy locally is 0. And analogously, this thing is a pure state in the B space, and so I can do the same thing over here. It's just that my two bases, my A and B bases, will be rotated with respect to one another. Okay, so what about the final thing? 3 question marks. So we need to understand more precisely. I said I was being a little bit hand-wavy here. We need to understand a little bit more precisely by what we mean when we say ignore one of the subsystems. And we're pretty comfortable doing this classically, but we need to be more, well, careful here. So how do I go from a composite system over A and B to a system over just A? So the argument is, given some set of measurables on system A that you know and love, we define essentially, or postulate, that the corresponding set of measurements on the composite system can be written down in this way, where this is just the operator, outer product between this measurement operator and the identity on the B system. And this is, I think, seems very intuitive. It's hard to imagine what else it could be. Okay, we have this joint state. We have postulated what these measurements should look like. So we know via the Born rule in this joint space how to compute probabilities of things. Nothing has changed there. We just have some measurement operator, joint measurement operator on our joint space, and gives us one of these measurement outcomes, or the probability. And so we can just backtrack and we can say, what must the state have been in order to correctly correspond to this set of measurement operators here? And this is defined by, this uniquely defines this operator here. This is really kind of the arrow here. This trace B is the partial trace operation that takes you from the joint space to the to one of the single spaces. Okay, so that's what this trace, partial trace, has to do. So this is a trace, and you say that this is the partial trace with respect to subsystem B, which means that you want to ignore subsystem B in order to maintain subsystem A. Just one sec. And so here's then the definition of what these partial traces are. So all you do is, given some joint space, joint state that you want to ignore all of the B aspects, you simply sandwich this thing with all of the inner products in the B space, or using any old basis that you like in that B space, and you add all these guys up, and then analogously for ignoring A. Yeah, Greg?
We just go back to the first slide.
Sure.
Previous slide real quick. So is the argument here that rho A is a density matrix that behaves like kind of perfectly adequately to describe A, given that it has to measure in this right way? I mean, it's like this is, the argument is that rho A contains all the information about probabilities for measurements on A.
Mm-hmm.
Okay.
I could have made this diagram a little crazier, but the thing that we're after is these things. So if we can get these things, then I guess this is, I don't know if this is a postulate of the quantum theory, that the density matrix contains those and only those pieces of information which are required for obtaining the results of any measurement within this permission operator space. So anyway, that means that if you know these and you construct something that gives you these using the operators that you think are the right operators, then this must be the right thing, the right state.
So this is a 2D stuff, but like, so this would cover like every possible projective measurement on the joint system that corresponds to a projective measurement on just A. So you have an example measurement.
Mm-hmm.
Is it that rho A covers your basis for every type of projective measurement on A, or is it, you know?
Let's see. So it's true that rho A, it's true that this trace operation is independent of the choice of measurements. Whether or not you can go through this proof with any set of measurement operators to force it, I'm not quite sure. I think you just need them to be complete. Does that answer your question?
Yeah.
Okay. Okay, so now we know how to ignore subsystems. All we have to do is sandwich with these things. So let's do an example. This is our mystery state over here that we need to understand how to construct this diagram for. So all I did was I took that and I represented it as a density operator by doing the outer product, and then we get distribution. Okay. And so let's ignore subsystem B. So what we do is we come in with, let's say, the computational basis for B, which to keep things easy, and then we add up all the things that we get out. So if I come in with a 0, 0, like this, I'm getting that 0 and that 0, and each of these gives me a 1 in the inner product. So that adds, when I do this, that means that adds to my total sum the object that remains, which is this 0 cross this 0. So there will be a 0, and those are existing in the A space, which is the space remaining that I'm looking for. Okay. Then we do it again over here, 0, 0. This 0 meets this 0 and gives me a 1, but this 0 meets this 1 and gives me a 0. So this contributes nothing. Same here. This 0 meets this 1, contributes nothing. And then here, 0, there's nothing contributed. So the sum over I equals 0 gave me just this term, 0 outer 0 with a half. You do the same thing with one sandwich with 1s, and you pick up this term with a 1, 1 and a half. And the result is this. Here's that 0, 0, the half, and the 1, 1 with the half. And it turns out that you get the same thing either way. Okay. And so what does this mean? Well, first, oops, geez. We know what these von Neumann entropies have to be. And we know this because we know here we go. We know this form of the von Neumann entropy. When we express the density operator in its spectral form, where we have the unitary, diagonal unitary form, then these guys are just the diagonal elements of that, or the diagonal elements, right, of the diagonal matrix. So here, sorry, here I have that. 0, 0, if you like, is the upper left. 0, 0 is this term. 1, 1 is this one. I have zeros on the off diagonal and a half out front. So it's easy to diagonalize this matrix and find the lambdas and take the entropy over this distribution, which is just 1 bit. Okay, it's just the entropy over this. Okay, so we've got 0 bits of entropy for this thing because it was pure, 1 bit here, and 1 bit here. Did I do that right? Nope. So what does that have to look like? Well, oddly, it has to look like this. So we have to allow ourselves to employ negative conditional entropies, which is a feature new to quantum correlations. Okay. I think I might skip the entanglement stuff. And if we have time at the end, we can come back to it and talk about it, because I wanted to make sure to get through some of the more research stuff. So can I just do that? Great. All right. So as I said at the very beginning of all of this, the goal is really to just take computational mechanics and quantize it, whatever that means. And that's really the main question, is what does that mean? Defining the parameters of that question, and defining what, when you make what choices, what interesting things come out. So the beginning of this section is, you're pretty familiar with, but I'll just kind of more for the camera maybe go through these slides so that they're there. We want to ask questions like, what is structure? But here, what is structure for quantum processes? And then we want to understand the relationship between the representations of a particular process when thinking of this in terms of a classical versus a quantum substrate. And then something that we might get to is this connection to the cryptic order, which you guys are familiar with from this class, which is kind of a funny thing that it pops up in this quantum context. And then if we have time, we'll talk about the trade-offs. Okay, so you all know what a stationary stochastic process is. I think we have pretty similar language here. The goal of the epsilon machine, or the goal of maybe anyone, is to predict the future, use some knowledge about the past in a hopefully compact way to measure or to predict the future. And you can do this with the infinite past, but of course, we'd rather do something like build a model. We can take advantage of redundancies in the relation between past and future to build models. Should I go through this in any detail? Okay. So this is a little bit of a more general picture before you collapse down into the epsilon machine picture of the relation between the past, the future, and some model. And so what does this mean? Well, this pink bit here means that or if there exists any non-zero conditional mutual information here, then that means that your model is somehow not capturing the entire relation between the past and the future. So we want this thing to be 0. And the amount that we're able to gain by using our model in predictions of the future is this piece here, which is the predictive gain. This is considered outside information that you can't have access to through just observations of the past, and in many instances that's a reasonable thing to assume. And so if we make all of those things appropriately 0, we find ourselves at this epsilon machine diagram that you are well familiar with, where we have the excess entropy here, the crypticity here, and then the sum of these two things is the statistical complexity. And that's kind of arguably the one of the broadest features that you can claim as a measure of the size of the epsilon machine. And so we're going to take that as our first go at defining an analog in the quantum context. So we're going to try to define essentially the quantum statistical complexity. Okay, these things are all familiar to you. These are just some examples for people who need some examples, but you've all played with these plenty. You know all about them. You know that CMU is 0.918, of course. Okay. All right. A little bit of, let's see, how much did you guys spend on Markov cryptic order? Some? Okay. Maybe I'll give you a slightly different take. All right. So the Markov order. The Markov order is defined as the minimum R such that this conditional probability is equal to the one where you replace the infinite past by some finite past of length R. Okay. And here it's written in terms of entropies rather than probabilities. And I'm just going to use this example down here to illustrate what's going on. Okay. Have you guys looked at these types of diagrams before? Maybe once? Okay. So we've got here all of the different states, and then these are the 1, 2, 3, 4, 5, 6 different words of length 3 that we can see in this process. There are only 6 of them. And then this diagram indicates what happens to all of these various states, or the potential for being in one of those states when I observe each of these symbols sequentially. So, for instance, if I begin in a naive state of being in all A, B, C, D, and E, and then I observe a symbol 0, I know that if I was in A, then I'm now in B. If I was in B, I'm now in C. And then if I was in E, then I couldn't have been in E. So I'm now nowhere. And so pushing this forward, you see that at this point here, before the last observation of 0, I could either be in C or D. Observing a 0 means that I'm now in D, and I know precisely where I am, so I've synchronized. So that means that they're in any word that might precede this. There's no point in going further than this in terms of obtaining complete causal predictability. Okay, so we do this for all the different words, and what you find, I'm labeling these as rejections versus mergers, and what I mean by that is the mode of obtaining synchronization can be different. So upon seeing this last symbol, we go from being in potentially 2 states to 1 state. And the reason that we go from 2 to 1 is because one of these paths is rejected or terminated. Whereas here, we go from the potential being in 2 states to 1 state, but not because they were both rejected, but because they both merge. And you see that merger here, merging on a 1 is right here. So E on a 1 and A on a 1 merge to A. Okay, so 2 different ways of coming to a state of synchronization or a state of knowledge. I'm just marking the point at which we have synchronization for each of these words, and then we just pick those that have the maximum length because that's what we're interested in here. We want the minimum R where we have to consider the max over all words of a particular length. Okay. The cryptic order then, in a sense, amounts to conditioning on the future, which in turn amounts to ensuring that you have a complete path, which is another way of saying that you're not interested in these termination type events. And so I just highlighted all the events that are of merger type. And when you do a similar marking of these things, and I'm marking these guys now with green triangles. So here, this green triangle indicates that that in this cryptic sense, conditioned on this future word, I don't actually have to see anything in order to know that in order to be synchronized to the machine, which is kind of a bizarre thing to think about. So now I can take, again, the max of all of these things, and you find that that's 2. So 3 reduced to 0, 3 to 0, 2 to 0, 2 to 1, and those remain at 2. So the cryptic, this is a way of showing that the cryptic order then is 2. Okay, here's just another way of visualizing what the cryptic order means. So you might have access to the entire past when attempting to predict the future. The Markov order says I can get by with this much when I'm trying to predict the future. The cryptic order says, well, if you give me this for free, I probably don't need all of this anymore. I can probably get away with somewhat less. And how much less? That's the cryptic order. So we should just say that first, right? Okay. All right, so in order to set up this problem in the quantum context, let me say a little bit more specifically what we mean in the classical context. So how do we interpret C mu? How do we interpret the statistical complexity? Well, it's the entropy over the states. Well, what does an entropy mean? One interpretation of an entropy is it has something to do with coding cost or communication rate. So what communication channel what communication scenario could I devise such that C mu would be the appropriate rate? Well, this one here. So Alice has some machine, it's bouncing around, it's in some various states. She stops it, she looks at it, it's in state A or state B. Bob's over there waiting to see what Alice says. And Bob would like to know what state Alice is in. So if there's just one thing to communicate, she would just send on over the letter A. I'm in A. And then he would know. I'm not sure what that is. Okay. Now we want to imagine doing this many times in parallel. So Alice has a whole bunch of these things, or maybe many people have a whole bunch of these things. And the distribution of these is the distribution of the stationary distribution over states. And I want to keep track of which one is which. I don't want to know that there's just a certain amount of these guys and a certain amount of the B's. I want to actually know that the first one's A, the second one's B. Okay. So I have this giant list of A's and B's, but then I want to take that message, and instead of just sending it raw to Bob, I want to compress it. And we know that the rate of the size of the resulting message when compressed optimally is of size n times C mu, and the limit is n goes big. Okay, so that's where C mu comes into this classical picture. Does that make sense? Okay. So we're thinking of C mu here as a synchronization cost or synchronization rate cost. Bob syncing through this channel to Alice. All right. So now we have to actually do some quantum mechanics. Now we actually have to attack this question. So how do we quantize this thing? Well, how do you quantize anything? You put the word quantum on it, and then you sell it for more than it's worth. I need to get better pictures on those. They're a little bit grainy. Okay, so here's the intuition for how we're going to try to quantize this particular model. Now let's look at what this thing does. It's got two states. It's symmetric. If you're in state A, you can either output a 0 or a 1 with some probability, p or 1 minus p, and B outputs a 0, or a 1, similarly, p or 1 minus p. But the p's and 1 minus p's are flipped. Here p goes with 0, here p goes with 1. And now the most important thing to note here is that as p gets very close to 1/2, this thing is very nearly the fair coin. So what does C mu do as a function of p for this particular process? Do you think? It might be nice if it went to 0. As we're close to 1/2. C mu is always 1 except at the point exactly p equal 1/2. Just draw it. So this p is from 0 to 1. And this is 1. Okay, so no matter how close we are to this point, p equals 1/2, where the thing is nearly indistinguishably a fair coin, the epsilon machine tells us that we still have to hang on to 1 bit of information. And this isn't necessarily unreasonable. We're asking a lot of the epsilon machine. We're asking it not to be a pretty good predictor. We're asking it to be a perfect predictor. And so sometimes perfection has a cost. But here we are re-examining this question in the quantum context. And we want to say, well, when we're really close to p equals 1/2, the future according to this state is really similar to the future according to this state. So in some sense, these things aren't really orthogonal anymore. And taking that literally, can we use that to express these two different states as non-orthogonal quantum states? That's the idea. So we propose this definition of quantum states that correspond to these classical states. So I take each particular classical causal state, like A or B, and I make a new thing, a quantum thing, and I construct it like this. I start in the, let's take A, state A. So I start in state A. I look at the probability of all words that can follow that state, and all of the causal states that are the result of following that word from that state. I look at that probability, take the square root, and then I tack on these kets that are in a space that represent this word space and this causal state space. And we use these to basically store the information about the probabilities in correlation with the words that they represent. Okay, so what does that look like in a little bit more detail? So for our particular example, the quantum state A has, well, I start in state A. The probability of seeing a 0 given state A, it goes in here under a square root. And then this thing here means that, or this thing is a quantum label for this particular word that I've seen. And then this thing labels the state that I end up in after having seen this word following this state. And we just do this repeatedly. The probability of a 0 given an A, probability of 0 given A is just P. So we have root P, 1 minus, or root 1 minus P. And then these things reverse. Okay, and what do we notice here? Great if I have it on the next slide, no? What we notice is that in this representation, so this is at least a hint that we're on the right track. In this representation, there's a non-zero overlap between these two quantum states. So in our classical thinking, these two things are orthogonal. And in this, at least in this representation, if it means anything, these things are non-orthogonal. And you can see that because both of them have some amount of A-ness and they each have some amount of B-ness. And you can see that when P becomes arbitrarily close to 1/2, that this overlap becomes arbitrarily close to 1. Okay, so we defined a set of quantum states, made up some definition, put in some probabilities, showed that there's some non-orthogonality there, big deal. So what does it do? Yeah.
Do you have any intuition for this construction of quantum states? Sort of just pulled it out of thin air here. If you don't want to go into it, it's like complicated.
Maybe let's look at the next slide and then ask me again. Okay, so here are those states again. So what can I do with these states? If I give you a state A to A, what can you do with it? Well, I can perform a projective measurement, and I can find that here I'm using a little bit of a different notation from previously, but I'm going to project in this it says state space. Yep, that should say word space. So first I'm projecting in the word space, which means that I'm coming in with remember my words are either 0 or 1. So I'm coming in with a 0 and a 1 here. These are my projectors. And let's start with state A to A. So if I come in with a 0 here, I pick up something from this term and nothing from this term. And this is I get a P out of this, and the probability is just the square of this amount. So I find that the probability, at least according to these rules that I'm making up, of seeing a 0, meaning obtaining quantum measurement result 0, given this quantum state A, which is the analog of causal state A, is P, which is the same as the probability of seeing actual word 0 given actual causal state A. So there's a correspondence here, which of course is by the construction. So what does this mean? It means that this thing can produce the right set of next symbol probabilities given the appropriate causal state input. So it's doing something right. Okay. And then this was, I didn't get into the details of this, but there's this L here. And this L means that this is a choice. I parameterize this set of states by a length L of words into the future that I'm going to use to construct these causal states. And so the previous example I just showed you used L equal 1. When L is something non-zero, this is no big deal. We just project using that bigger word space. So the kets are some word of length L. We obtain the probability of that word given that causal state. And then what we do is, since this projector with a particular word has essentially met and annihilated with its partner word here, this causal state, ket, or this quantum representation of the causal state, then is carried on as a byproduct. So this is kind of a tag-along. So this inner product gives me the correct probability, but then the fact that this quantum object still remains, meaning that the quantum space is still bigger than I haven't projected away everything yet. I've only projected into a subspace. It means that I still have something quantum left. And what I can do with that is I can measure trivially in this quantum space and obtain the name of that state, which is exactly the name of the quantum, the classical causal state that it corresponds to. And then I can use that thing to go back to my big machine that makes these things and make another one with this thing as the input as opposed to this thing as the input. So I can just repeat the game. So in sum, this procedure works for any L, and I can iterate, I can produce symbols for as long as I like. Okay.
I have a question.
Yeah.
So I kind of just assumed it was right, but so you're assuming that those kets in the word space are all orthogonal?
Right. I didn't say that explicitly, but yep. Mm-hmm.
So I don't know.
We designed it like this.
Yeah, but so for example, a word like 000 and 001 are less orthogonal than a 100 word, right?
Okay, that's an interesting question. Yeah, so you could maybe try to use that to attack what happens when you have some distortion in your in the transmission. That would be an interesting thing to pursue, and we haven't done that. So yeah, right. They're exactly orthogonal because we're demanding perfection.
Right.
But yeah, that's a good point. And then depending on the kind of distortion you wanted to think about, that would inform how you thought about the non-orthogonality like maybe, bit flips are close in one context, but maybe deletions or something are close in another context. Okay, so now we're going to play the same game quantumly, and Alice, instead of sending A, she can use her big quantum thing to turn this classical knowledge of state A. She presses the A button, and it produces this quantum object, which is in this state, A to A. And then she can send that to Bob over her quantum internet. Similarly, if we do this a bunch of times, then we can take, instead of all these classical symbols, we can take all of these quantum states, and we can compress these, as was claimed last time, into a message that is of size n CQ of L, where this is defined as the von Neumann entropy over this ensemble as opposed to the Shannon entropy. Oh, and there we say it. So again, everything is parameterized by L, and we haven't really talked about what that means, but everything works for any L, so for now it's just a free parameter. So the CQ, the analog of C mu, is defined by the von Neumann entropy of the ensemble, which is the probabilistic mixing of these various etas, A, B. And so we would write that. Oh, I did write it. This ensemble here is the probabilistic mixture of these eta guys. And the probabilistic mixture that we use, or the particular mixture we use, is the stationary distribution, because that's stationary distribution of these, which is deterministically giving us again, it's a quantum negative, sometimes it's there. All right, so let's use this construction and analyze a couple processes. So here again, we have this thing that I used to kind of motivate this whole construction in the first place. And this is a complicated figure, so let me walk you through it a little bit. Let's start on the right. So for a particular P, I guess I've chosen 0.666 or something here. We find that the classical cost, which is C mu, is 1, as we knew. And the mutual information is something here like 0.08 or something like that, which is the excess entropy. Okay. We find that CQ, our quantum measure of communication cost, at length 0 is trivially the same as the classical, but at length 1 drops down dramatically from 1 to about 0.2. Now we can keep cranking this up. We can keep cranking up L, but unfortunately we find that there's no further advantage. But this is great. We've got an 80% win in some respect by considering this quantum representation at this particular p-value.
Don't forget, this is not just one bit. When you repeat this like 1 million times, this is 80% advantage.
Right, 80% is a better way of saying it. Yep. Okay, and so now pulling this back here, this is just one slice of this plot here for the particular p equals this. We can do this for all the various p, and we find that the statistical complexity here, like we know, is always 1 except for the center point. The excess entropy dips down like this, with its minimum here in the middle, and the CQ, the quantum complexity, at least for today, does this, where it's bounded between these two curves, and it kind of looks more like the E than it does like the C mu, which is kind of interesting. So I guess general takeaway, there's even in this kind of simple off-the-shelf system, there's a big advantage to using this quantum representation. That big advantage is pretty generic over all probabilities, and we only have to go out to L equal 1 in order to make this work. Any questions so far? That was a lot of information.
Is there an E-mean by the definition, the way we calculated the mutual information before, for the quantum? two systems. Is that the E mu and that C mu still will be not less than that E mu?
E mu. Do you mean excess entropy?
Yeah, that X entropy is for the classical system, right?
The excess entropy is for the classical system, yes.
Can we do a quantum analysis of that?
You can, and you can show that it has to be the same. Yep. But that's a good question. Okay, so going on, let's go to something a little bit more interesting. So you guys, I think, looked at the RK golden mean, which is a nice way of looking at processes that have a tunable Markov and cryptic order. And this one, I think, has Markov order 4, cryptic order 3. I hope. So for some probability p, I think it's a half, we go over here and we look at what we've got. The classical cost C mu is here, 2.7. The excess entropy here, about 2. And we find that the quantum cost decreases pretty much linearly with increasing L up to 3, which happens to be the cryptic order. And then from then on, there's no further compression or no further quantum advantage. And so we get a little bit of improvement, more improvement, the most improvement. And then this is just illustrating that same thing for all the p's at once. A little improvement, more improvement, the most improvement. And you can see that these have similarly this nice nesting. So the point of this is that we can, by going out to longer lengths of encoding or construction in this quantum construction, we can find more advantage by cranking up L in some kinds of systems. And it appears to be the maximum or the saturation of this advantage appears to occur at the cryptic order. Okay. And then here's one final example, the NEMO process. This is kind of interesting. Initially, we have this very large quantum advantage, a little bit more, and then almost nothing. And then again, a pretty significant advantage, at least relatively. So this is illustrating that this thing can have a very non-trivial shape. We do have some results about what that shape can be, at least asymptotically, but certainly we don't have any kind of convexity here.
But it's monotonic.
That's a good question.
Unfortunately.
Yeah, unfortunately, it's still a good question. Yeah, so the result is there that we've computed now, I don't know how many million of these curves, and they're all monotonic in CQ. And we don't have a proof of that particular fact. And exactly why that's true, I think, would take a little bit too long to explain right now.
The interesting thing is there is a parallel problem in quantum information theory that people think about and it's still open. And if you solve that, you solve this. Okay.
Yeah.
So it's not that easy.
Right. And there's also, yeah, I'll come back to that maybe in, well, no, I'll just mention now. So there's also an interesting fact, also only semi-proven, which is you guys have spent a fair amount of time, I think, thinking about forward and reverse processes. So you've, stay over here. So if you have a past and a future, you construct your causal states like this. This would be S plus. And you generically find that S minus can be different, right? And I guess by sampling, it's typically bigger when you, by pigeonhole. Okay, so what do we find quantumly? Well, or at least according to this construction, what do we find? So here's our S plus and S minus again. I don't have colors. Then we find that quantumly CQ, and let's say here what I mean is CQ min, called CQ bar, is equal to CQ, this is CQ plus bar and CQ minus bar. These are equal, even when these are not equal. And like I said, interesting fact, or numerical fact. We have some ideas about how to prove this, and it's also maybe related to this idea of the monotonicity. But we have to, there's some work to be done there. So if anyone wants to work on that, think about it. That would be great.
Way of looking at that like a bidirectional quantum machine.
That's one of the strategies, yeah, is to construct a bidirectional quantum machine and somehow derive this as kind of a trivial consequence. So, yep, good suggestion. Okay, and then I think, well, I'll just say a little bit about this. Okay, so as you saw in our definition of the quantum states, we have something that looks like eta j equals sum over words and some probability with a square root, and then we have this word here and some state there. Okay, well, as we go to longer and longer lengths, these words become longer and longer, but there become exponentially more and more of them. So the Hilbert space that we're embedding this thing in becomes exponentially bigger and bigger. And computationally, if you want to use some kind of, say, quantum, not quantum computing, but computation of quantum stuff in Python, you end up working with extremely large matrices. That's kind of the naive thing. Exponentially large. So for instance, we saw in the NEMO process, we didn't really get decent convergence until we're out at like 8. And this is for a 3-state machine. It's easy to make things hard to converge to till, however long you want to go. So naively, this is a real challenge. It turns out that, and it's actually simple to show, that while the space that this is being embedded in kind of naively grows exponentially, the span of this set is actually only ever finite in size inside this exponentially growing space. So if you can somehow just focus on that span and carve it out of this exponentially growing space, then you're only ever dealing with a fixed size matrix, essentially, for doing these computations. And so that's kind of the upshot of the evolution of the 2 recent papers, the Occam's quantum strop, and then the now called minimized state complexity, right? Is that we have not only a way to do this in the reduced state space, but we have a way to do this analytically, numerically analytically. So we do everything up until computation of eigenvalues, or yes, eigenvalues analytically. So now we can compute things. I could have demoed this. Maybe I can demo this for you after class or something. But we can compute these things out to L equal, 1,000 in no time, which is pretty cool. And then without going into the details, I'll just say that the algorithm, or one of the algorithms that we use for computing these things really quickly, makes use of a transient structure. And so, and moreover, this transient structure is kind of related to the transient structure that you use to compute the cryptic order. And these are the examples for the particular three, or these are the transient structures for the three examples that I showed you earlier, the bias coin, RK Goldamine, and the NEMO. Just a very simple one.
Amber Alert.
You okay? Okay. A simple one, a nice tree, and then one with a little loop in it. It's this loop that makes this thing never converge, but just converge asymptotically. Anyway, I guess maybe the broader point here is that it's the recasting of the problem in terms of the appropriate transient structure that allows you to attack this problem really cleanly. And I think we've seen that come up in a variety of different contexts in terms of computational Markov order, cryptic order, and I know there are all kinds of things going on with the exact sync, computing your favorite, everyone's favorite quantity, and it really, I think, all amounts to the pre-processing or the setup of the problem in terms of the appropriate transient structure, and then after that, it's just whacking it with linear algebra. Yeah.
You want to explain a little bit about ambiguity of simplicity
No.
as a context of class?
Do you?
No.
Okay. Okay. And the point of this slide, you've seen this one before, I'm sure, or maybe at the end. The point of this slide is this was a talk introducing this kind of stuff to people that had never been exposed to the notion of cryptic order before, and so what's the big deal? And then this slide is intended to impress upon people that processes with big cryptic order are everywhere, and so these are the main thing that we have to think about. And so being able to compute this CQ function accurately and quickly for large L is critical, because it doesn't converge until we get to the cryptic order, which is generically infinite. And then this, I'll just give you kind of a flavor for this slide. This is kind of a big discussion in and of itself, but we'll just say that there's some question as to how to best phrase the relationship between the classical and the quantum setup. So I showed you the picture in terms of Alice and Bob. Alice is communicating to Bob. But precisely what it is that Alice is communicating to Bob, you have to think about very carefully. So in the classical context, when Alice gives Bob a particular state like A, or when she gives him this message which is compressed and then he decompresses it and sees A, he has the ability to predict with that state, meaning that he can plug it into his epsilon machine and he can compute a complete future morph for all the probabilities of all words starting at that causal state, which is the same as the causal state that Alice is currently staring at. So they have equivalent future morphs. Not only do they have them, but they know them. And that's the difference. They have them and they know them. The difference here is that Bob has the same future morph, but he can't know it until he does a measurement. And the measurement causes the particular quantum state that he's been given to collapse. He can't reproduce another one to perform new measurements on, to kind of build up an intuition about what that morph looks like. So he's able to do some form of prediction, but not as complete as Alice can do. And so this causes you to think carefully about what it is exactly that Alice is communicating. And maybe I'll just leave it at that. But
one of the important difference between classical physics and quantum physics is, if I give you a bit, you could measure it n times and know that this is 0 or this is 1. But if I give you a quantum state and you do the measurement, your quantum states change. So the question is, can I copy it before I do the measurement? And the answer is no. There is no such a thing as perfect cloning in quantum mechanics.
Yep. We didn't talk about that. Maybe for the people that haven't done quantum before, that's a neat and novel fact. This no cloning theorem. So yeah. And this boils down to just making use of the post-measurement states that we defined. So given a particular input state, we talked about how to compute probabilities of particular outcomes, like this. And then we also talked about what the post-measurement state has to look like in terms of this projector, where it's normalized. This state is different than this state. And without knowing this state a priori, there's no way of going back. So once you're given a state and you make a measurement on it, you have some partial information about the input, but you can't recover full information about the input. And so what Senna was saying is that, well, you could try to be sneaky, and before you make your measurement, you could try to clone these and make 2 of them. And there's a very simple proof that shows why you can't do this. This is disallowed, and the gist of it is that it's unitarity that prevents this operation. So I think that's the end of my story. But there's a lot of research to be done. We're actually just kind of at the beginning of this. We have about a half a zillion questions. And a lot of them these days have to do with well, there are a couple different camps of questions. One of them has to do with the idea of representation. So you've talked a little bit about the epsilon, or a lot about the epsilon machine, but you also are aware of other representations, other non-unifilar representations, representations with, say, gauge information, the bidirectional representation. And so, well, stick a Q in front of it and ask analogous questions is kind of one approach to this. So what do all these things mean when you quantize? And there's some interesting preliminary results there. Some of the things that look like redundancy in the classical representation don't look like redundancy in the quantum representation. Somehow the quantization seems to naturally handle some redundancy without any further specification. And that's kind of an interesting thing that we don't fully understand. And yeah, a zillion other questions, but you can maybe come talk to me if you're interested in hearing more.